This video is about the empirical rule, which I think offers an easy interpretation of the standard deviation. A couple notes first. The data must be normally distributed, so in order to apply the empirical rule, you must have normally distributed data. Second, x bar, which is the sample mean, is an estimate for mu, which is the unknown population mean. And third, s, which is the sample standard deviation, is an estimate for sigma, which is the unknown population standard deviation. What the empirical rule actually says is that 68% of the data is going to fall within one standard deviation of the mean, so that gives us this range. X bar minus s is the lower bound, x bar plus s would be the upper bound. 95% of the data will fall within two standard deviations of the mean, which gives us this range. And essentially all of the data will fall within three standard deviations of the mean, and again that'll give us this range. This all is actually 99.7%, but for the purposes of this class, we can just say that it's all of the data. We can think of this in terms of the normal curve, something like this. So their x bar is going to be in the middle, and then moving to the right, we're just adding a standard deviation each time, so plus s, plus 2s, plus 3s, and moving to the left, we're subtracting a standard deviation each time. Empirical rule says that between here and here, we're going to have 68% of the data. Keep in mind this curve is symmetric, so in each one of these slots, there'll be 34%, which is 68 over 2. From here to here, we'll have 95% of the data, and then from the third standard deviation all the way over, there we're going to have approximately all of the data. So we can break this down a little bit further. Remember I said that here and here we're going to have 34%. We'll also have 13.5% here and 2.5% here. Same thing on this side. You don't have to memorize these percentages, but it might be helpful. Like this 13.5% can always be derived. Where this comes from is 47.5 minus 34 is 13.5. That 47.5 is 95 divided by 2. So from, let's say, here to here, that's 47.5%, because that's 95 over 2. If from here to here is 34%, then what's left has to be 47.5 minus 13.5. How can we use this? How can this be applied? So I have some data and then a curve. So this data represents pitch counts, Greg Maddux pitch counts. Let's just assume that the data are randomly selected. They weren't, but let's assume they were, and that the distribution is approximately normal. So we need some summary statistics first. For this data set, the mean was 84.97, but let's just say it's 85 for the purposes of addition. And the standard deviation, 14.95. Let's just round that up to 15. So filling in the curve, 85 is going to be in the middle, and then we're just going to add one standard deviation this way, so 100, 115, and 130. Subtracting a standard deviation going the other way, so 70, 55, and 40. And then a question we could ask, maybe something like this. So what's the probability that Maddux throws between let's say 100 and 130 pitches? So we're looking at that part of the curve. And if we use the first curve up here, we know this section is 13.5. We know that section is 2.5. So we just have to add those two percentages together. So there'd be a 16% chance that Maddux throws between 100 and 130 pitches. So that's what the empirical rule is, and this is, I guess, kind of a simple application.